So I'm Christoph. So I'm the one who started this Q2 VKPT project, and in this talk we will first talk about Q2 VKPT and then the extensions that NVIDIA did on top of the Q2 VKPT code base. And so Q2 VKPT, a very nice acronym, so this is Quake 2 Vulkan path tracing. And since we will be talking about path tracing a lot, I just want to give a very brief refresher on path tracing. So path tracing is a method for constructing light paths, and it's a physically based method. And it works by starting from the eye of the observer. And so you cast a ray to find the primary visible surface. So this is also what you would do with the rasterizer in a game. And then at the hit point, you perform next event estimation. So this means that you stochastically select one of the light sources. And these can actually be physically based light sources, like area light sources of any shape. So you take all candidates and you perform a stochastic sampling, and you have one candidate to actually compute the shadow ray. Next, you compute the scattering event. So this means that you import and sample the BRDF to have the material properties. You get a random direction to continue your random walk. And again, you find your hit point. And now you do for this indirectly visible surface, again, the next event estimation by finding all the suitable light sources, selecting one randomly, and computing the shadow ray. And this process goes on and on and on. So this is basically like an iterative or recursive process. So you can think of this going on forever until you have reached the depth that you want to achieve. And so this is a stochastic process, so you get these random light paths. And to get the actual correct result, you would need infinitely many samples. And of course, you cannot afford that, so you would just use a limited budget. And in Q2 VKPT, we were actually using only one sample per pixel, or one of these stochastic light paths. And so, as probably everybody knows, the biggest problem when you do path tracing is how do you actually deal with the noise. So each of these random decisions that you take actually increases the level of noise. So it's actually a way higher level of noise than what you would do if you just sample, for example, the indirect illumination in a game right now. And so you have two angles of attack for countering this noise. So first of all, you can improve the sampling techniques. So with perfect importance sampling, there would be no noise, but that's not possible. And also you can use denoising filters to remove the remaining noise. And so I started Q2 VKPT as a research project. So I've done research on denoising or reconstruction filters. And so I wanted to figure out like what is actually the current state of the art if we want to do path tracing in real time. Like, can these denoising filters really deal with this fully dynamic content, like going further than just a standard research prototype? And so this is completely open source. So if it's open source under the GPL, it's roughly 12,000 lines of code. I wrote it in about 2 months, and it's a completely ray-traced engine. So the renderer was completely replaced, and it's based on the Vulkan extensions by NVIDIA for using RTX. And so here you can see a short video sequence, how the game actually looks like in practice. So you can see we have water reflections, we have these explosions, and these explosions actually also act as area light sources. You can see these nice smooth shadows outside here that are actually cast by the environment illumination. And so everything that you see here is computed fully dynamically, so there's no pre-computation of the light transport at all. And so all of these light sources that you can see here, so they have these nice glossy highlights on the floors, and everything is stochastically sampled here. And everything is casting soft shadows. And also things like these doors opening here, you would see like these dynamic shadows, or from these explosions here. Okay, so in terms of performance, here you can see a breakdown of the Q2 VKPT profiler, and so we achieve roughly 60 FPS, so it depends on what's going on. So water is expensive, and if you have dynamic explosions, then it also can drop lower than 60 FPS. But still, it's a fairly reasonable performance. And of course, the main part of the runtime is the path tracer itself, and the denoising is the next strong candidate. But you can see like a full denoiser for path tracing is possible in 3.5 milliseconds at 1440p. And so things like BVH updates and instancing of the geometry, of course, is very cheap and trivial for us since we are only dealing with Quake 2 assets. All right, so now I want to talk about the denoising part of the project. And so the denoiser would see this as an input. So this is like the raw output of the path tracer, and you can hopefully see that it's very noisy. And so the denoiser will just swipe away the noise for you and give you these nice images. And so here we'll flip between the denoised result and the input. So you can see denoised. This is the input. And I would say it matches fairly well. Of course, there's some overblurring, but I mean, there's only so much you can do with this coarse input. All right, so the denoising is, as I mentioned, based on my research. So this is the Spatial Temporal Variance Guided Filter, yet another great acronym, SVGF, and also the extensions for a better temporal filter. So this makes it then ASVGF, even better. And so I now first want to talk about how SVGF works on a very high level. And so it has basically two main principles. So first of all, it looks at the input that you pass to the denoising filter over time. And so if you look at this image on the left, you can see that you have like distinctive regions. So first of all, the full shadow, there's no noise, and you don't need to do anything in this region. Also, you have the fully lit parts, and these also you don't need to touch because they are already stable and are nice. It's only where the sampling actually changes over time that you want to perform the denoising. And this is what the filter uses as an input guide to actually figure out what are details, what is noise, what needs to be removed. The next principle is that it works hierarchically. So it starts with a small filter footprint, and then it iteratively processes the input. And so after each of these filter iterations, it does a new estimate of the level of noise. And so by that, it would basically kind of carve out these details in the noise. And so as soon as as it has achieved temporal stability, it will stop to apply blur. And this is why it doesn't overblur contact shadows, for example. So this is how the filter is added in the whole pipeline. So we have the path tracer, which outputs these very noisy pictures. Then as a first step, we remove the texture detail from the first visible surface. And by that, we get this untextured illumination. And this one is way easier to handle because we do not need to protect the texture detail from the denoiser. And so we can filter very aggressively. Then we remove the noise, reapply the textures, and have TAA for some edge anti-aliasing. And the filter itself consists of three parts. So first of all, we have this temporal accumulation. So this is a filter that increases the effective sample count by collecting data over time, but it also keeps track of the level of noise to actually steer the other parts. Then we have the variance estimation. So this is actually performing like this. It analyzes the image, how noisy it is, how strong the filter should be, and it also has a fallback if there's no temporal information yet. And lastly, we have the true wavelet filter, which then actually performs the spatial filtering. And the true filter, so this is based on a wavelet filter and you have your input signal, and you just perform a weighted sum of your neighboring pixels. And the interesting part are, of course, these weights. So these weights consist of the filter kernel H, and you also have edge stopping functions. So these are functions that are, for example, based on geometry, so that you wouldn't blur over depth discontinuities or have different surface orientations. But the most important one is actually working on differences of the luminance of the pixel, the central pixel, and the neighboring pixels that are combined. And actually, anecdotally, so in the version of Q2 VKPT that I shipped, all of the edge stopping functions were broken except of the one for the brightness difference, because the other one was only doing the right thing every other frame because of a very embarrassing bug. And so this luminance edge stopping function is actually what does the heavy lifting for protecting the details. Then this hierarchical filter scheme, so this is the true convolution. So basically you spread out your filter kernel, so you always have the same number of taps, but you increase the effective footprint by spreading out the filter kernel. So this is also fashionably called strided convolution in the deep learning community, because we always need multiple terms for the same thing. And yeah, so you spread out this filter kernel, and this means that you have always so each of the pixels in the previous iteration already contains information from a neighborhood, and this means that it's growing very rapidly, so you only need very few iterations. So this is what you see here, and in Q2 VKPT we actually only use a 3x3 filter kernel, so it's even the box kernel, and we use 5 of these filter iterations, and this is why it can be so efficient. Unfortunately, with SVGF there's a large elephant in the room, so if we look at an animated scene, like here where you have these moving occluders in front of a light source, then you can see that the shadows are actually lagging behind and they are not fully saturated. And that is because SVGF was only using a very simple temporal filter, because it turns out that temporal filtering is very hard for path tracing. And so this is what the next paper addressed. So this is the adaptive temporal filtering that replaces the simple temporal accumulation. And so this adaptive temporal filter is also a screen space reprojection technique. And so this means you have your current frame, you have your previous frame, and you have motion vectors that tell you in a backwards direction where your pixel of the current frame was in the previous frame, as you can see here. And then you just have this simple formula to weight the old image compared to your new image. So this is pretty much the same as in temporal anti-aliasing. What is different, though, is how these different events are handled. So, for example, if you have an animated camera, then you will have geometric disocclusions like here. And so this means these windows that were visible before, they became occluded. And so now the history for these pixels, of course, is not valid anymore. And so for that, we use geometric tests to just verify whether we are still seeing the same surface. But what's way more complicated is the situation when we have changes of the shading function. So for example, here there was a light source which was turned off, and also the glossy highlights, of course, move on the floor if you animate the camera. And so these are very hard to detect because you have this very high level of noise. But this is actually what we handle in this temporal filter. And so the general idea is that we, again, have this exponentially moving average, but we adaptively set this alpha parameter to be able to reliably drop history information when we detect that it's not valid anymore. So for example, if there's flickering lights. And we do this also locally adaptive, so this means that if there are stable regions of the image and unstable regions in other parts of the image, then we only drop the changed parts. And to make this work, we actually need to find information like how did this image or the shading function change over time. And so I don't want to get into too much detail, so it's a bit of an involved process, so please refer to the paper for that, but I want to give a few motivating examples how we do it. So first, here we can see the all-beloved Cornell box and a moving light source, and if we now just naively take the difference between consecutive frames, then we will get very high levels of noise. So here you can see color-coded whether it's a positive or negative change of the brightness of these samples. And you can see it's very, very noisy. And even more problematic is that even in the static configuration, if we do the same thing, then we will still see high levels of noise. And this will make this temporal filter completely unreliable. And in fact, this level of noise is even higher than what the original path tracer output had as a noise level. So we are definitely not able to filter this or denoise this. What we do instead is that we correlate the random numbers. So this means now for each pixel, you always have the same random number seed. And so now you have a stable pattern of noise, and if you now do the per pixel differences, then you can see these nice distinctive regions, and this is now actually a very useful information. So of course, now we basically defeated the purpose because we get no new information because everything is correlated, so each frame computes the same stuff all over. And so for that reason, in the temporal filter, we only correlate a small subset of the pixels, so like every 9th pixel at most. This gives us then a very noisy and sparse estimate of this temporal gradient, and we use a reconstruction filter that is very similar to SVGF to get a dense and relatively smooth image out of it. So you can see on the top image, there's of course still some artifacts and some noise. And we are actually not interested in this absolute change of the shading signal, but we are interested in the rate of change. So we have an additional normalization factor which tells us how much the image in this region actually has changed. And this is what then ultimately controls the alpha parameter. And this is what you can see here in this video. So this yellow means that it completely has dropped the history, and the purple part, or whatever the color is called, this is where it has accumulated lots of temporal history. And so you can see, first of all, the geometric disocclusions, but also like explosions that light up the pathways and the glossy highlights on the floor, that these actually show up in these gradients, and this is where the filter will drop the history. And if you don't do this, then you will have horrible ghosting artifacts that make this completely unplayable. All right, so much for denoising. Now I want to talk about the path tracer, so how we actually implemented it. And so here in this scene, you can see like it's actually illuminated by quite a few light sources. So here I've marked them for you. And each of these light sources consists of several triangles. And as I mentioned earlier, we actually handle area light sources. So this means we turn each of these polygons that we think are a light source, we turn these into an area light source. And the same actually also for the explosions. And so now this is still a somewhat manageable number of light sources, but you have to imagine if you would just naively randomly sample from these lights, then you basically have every 10th pixel which would see one of these light sources. And so this means that you will get very high amounts of noise. What is even worse is that we don't have a single room in a Quake level, but we have a full level, so we actually will have thousands of these light sources in practice. And so this means that we need to be a bit more clever. What we tried was to use a light hierarchy. So this is the standard approach in offline rendering. So you have a tree over your light sources, and you do a stochastic traversal with some random numbers through the light hierarchy. But unfortunately, I mean, this is a nightmare for the GPU because you just maximize like how divergent your accesses to the memory are. And also, we found that the quality was very inconsistent because if there was a rocket flying through the scene, then it would completely change the topology of the tree, and so everything would start to flicker. And so we went for something a bit simpler. So we used the potentially visible set from Quake 2. So this would tell us for a cluster of the map which light sources can actually be visible. And so we encoded this as a list to be part of the mesh on the GPU. And so we then stochastically sampled from this light list. So this can still be like 20 candidates or something like that. And so to make it a bit cheaper, we just stochastically select a subset. And then we actually perform a very expensive importance sampling on top of that. So we have a simplified version of the BRDF and also consider the projected solid angle of these triangles. And so we build a CDF from that we can actually sample. And so this means that we have a point-specific CDF, so the quality is actually pretty good of the sampling. And so after sampling the CDF, we have one candidate for the light sources. So this is what we do for the static lights that are part of these levels. And for dynamic lights, unfortunately, we don't have this pre-computed visibility information. And so we just don't do any culling because it's somewhat to be expected that the rockets are always close to the player and not somewhere else on the map. Right, so now we have this process to select between dynamic and static light sources, and we still decide or we only want to afford one of the shadow rays. So we now stochastically select whether we want to sample the visibility for the static or the dynamic light. And then we end up with one light source in the end. So our path tracer can handle one indirect bounce somewhat, so it's still missing one ray, so it cannot hit the environment map from the indirect bounce. But still, so we have to perform 2 next event estimations and perform 2 shadow rays, and also shoot the scattering ray to find the indirectly visible surface. And we also somewhat can handle glass, but there are some limitations in the reconstruction filter. And the same for mirror reflections. And we just ignore these materials for the indirect bounce. So here's a screenshot of the scene you've seen earlier. And so due to time constraints, I made everything just have the same BRDF. So it's just a Blin-Phong BRDF. So everything is rather metallic looking, even if it's grass or the enemies. But yeah, as I said, there wasn't that much time. And so there's no importance sampling for the environment map. So we just use this indirect bounce. If it hits the environment map, we look up the actual contribution from there and illuminate the scene with that. So at least we have direct illumination by the sky. And as I mentioned earlier, so we do this mirror reflection for water, but we do not sample the Fresnel term. So that's why it looks a bit metallic and weird. What is very important if you want to do good denoising is that you choose a very good sampling pattern. And so we use blue noise dither masks. And so for each random decision that we need to take, we have yet another blue noise dither mask, and we also have multiple of these for the individual frames that we cycle through. And so since we need to fill the whole screen with noise, we just tile this. And as you can see, it looks fairly decent. And so I want to motivate why we need this. And so first of all, here's what you can see if you just take white noise and if you apply a Gaussian filter to it, so a low-pass filter. So you can see there's still lots of noise left in the result. And this would be very unstable if you actually look at this over time. If we do the same with blue noise, though, then we can see that we have a much more uniform color. We have much less noise. And if we look at the frequency spectra of the noise, then it's actually very obvious why this is happening, because white noise has frequencies, like has the full spectrum, and blue noise has the low frequencies removed. And what we are doing to denoise is just a simple low-pass filter that is a bit more fancy to not overblur details. And so this means if with this low-pass filter, you cannot remove all of this noise if you're already starting with white noise. So that's why you definitely need blue noise or something similar. All right, now for some smaller implementation details. So we have two acceleration structures. So we have one that we built once on map load with the static geometry, and we rebuild everything from scratch for the dynamic parts because it's so few polygons that it's not worth to individually update the parts. For the temporal filter, we actually need to perform a forward projection for these gradient samples because we have to be very precise and cannot have subpixel offsets. And this was a bit more involved to implement, and for that we use a visibility buffer. So per pixel we store which of the triangles was hit and also the barycentric coordinates for it. And so this means we also need to be able to map from previous to current frame and the other way around as well, because we also, of course, need backward projection, just to make things more fun. All right, so with that I actually want to conclude. And so I think real-time path tracing is a possibility to a certain extent. There's, of course, still lots of limitations, but I think it's a very interesting field to explore. So what is very nice about path tracing is that it allows you to nicely have this scaling in terms of that you can allocate fixed sampling budgets. And so if you would have, like, let's say, more light sources or something, then you wouldn't degrade the quality. You wouldn't degrade the speed, but you would make compromises on the quality. And so you have all of these scaling things in path tracing that are actually way nicer than iterating over light lists. The transition is not very easy. So I mean, there are all of these special data structures, the forward projection, everything that you need. So that's why I also had to rewrite the entire renderer from scratch. And of course, you also need to tweak the assets to actually be able to use path tracing because it will just look quite different. And I think the current state of the art of research is already pretty good, but of course there's still so much you can do. So we need better importance sampling. Lights is definitely a very hot topic for more research. So we need better importance sampling, and of course denoising still has tons of limitations. So this is also something that we need to push further. And with that, I want to conclude my part of the talk. I want to thank everybody who was involved with the project, directly or indirectly. I also want to thank the Quake community who created nicer textures and kept the game alive. We used Q2 Pro, which is an improved engine. And yeah, I want to thank NVIDIA for actually inviting me to give this talk here. With that.
Thank you. So now I will be talking basically about what we did to make Quake 2 VKPT look like it does now, basically the transition from Q2 VKPT to Quake 2 RTX. And I will be mostly just telling a story, and it's not a very technical kind of talk, although I do have some technical details here. So we started with an image that looked like this. It looks interesting. I mean, you have nice shadows, you have all the specular reflections, but it still doesn't quite look right. Doesn't feel natural, right? And we tried to investigate why. One of the first things that we discovered is that Christoph used a texture pack in his work. That's for the better, but still, we were not sure of the quality of these textures. Like, are they physically based? Are they, what color space are in? Are they good? So we started by just removing those textures. and worked our way down from, up from the textures in the original Quake 2. And now, if you look at this picture, you can see actually some more very specific issues with it. One of them is that all the shadows on the left are very dark, although if you looked at a similar map in real life, basically, you would see that the light from the sky and from the local lights will bounce off the objects, and those areas will just not be as dark. So there's something going on there. Another thing is that the images of local lights, they don't exactly blend in with the environment, because that light on the left, it's probably just two triangles, and these two triangles have a texture, and they are tagged as an emissive object. So the entire texture is counted as emissive, although the fixture itself of the light should not emit anything. And finally, you can notice that the reflections on the floor are inconsistent with the image that we see reflected, because the local lights are quite dim compared to the sky, but their reflections are brighter than the reflection of the sky. So there is something up with either the reflection themselves or the material of the floor. And finally, the skylight itself is actually too dim, because in real life, the local lights, like artificial light sources, are typically orders of magnitude dimmer than the sun and the sky. So we tried to fix all that. The first thing was that we made the sky much brighter. And we also figured out that people are not used to see red or saturated, like red or yellow sky. And for that reason, when you have a red illumination from the sky, it doesn't look natural to you. So we tried to desaturate the environment map just by applying a very simple transform. That made the image look different, arguably better. And yeah, like I said, we just made the skylight intensity much higher, like I think 20 times higher initially. And you can notice that the shadows on the left the shadowed areas on the left are not so dark now, because we have more light from the sky. What we didn't notice at first, though, is that the shadows from the barrels here are missing now. And that's actually it was a big problem. And let me explain to you why is this a big problem, and let's look at this selected region in more detail before denoising and before textures. So this is what it looks like on the left with a dim environment map like it originally was. It's a fairly low noise signal where most of the lighting comes from the local light on the left of the barrel. But now when we make the environment map much brighter, we get this salt and pepper noise, what it's called. A fairly sparse subset of very bright pixels, because the size of the opening into the sky in this room is fairly small. But when a ray hits the sky, it gets a lot of illumination. So we have maybe something like 5% of the pixels here having those bright skylight illumination values. But on average, they make something pretty dim, because they're just 5%. So the problem with that is that when you have such mixed signal, it just messes up the denoiser. So what's happening here is that let's just plot the brightness over position, basically. It's a cross-section of the previous frame, of the previous slide. So when you have no bright environment map, we have these two sets of dots, which are stochastic samples of lighting from the local lights. One of them has some lighting on the left, but no lighting on the right, because it's a shadow. Overall, we have a fairly low variance in the signal, and as a result, the variance-guided filter has pretty low width. So it doesn't blur too much, and the shadow is preserved. And that curve on the left slide is what you get after denoising. It's a nice, sharp-ish shadow. But now when we add the skylight, which is bright but sparse, we get a lot of variance in the signal. So in order to efficiently filter that variance, we have to increase the filter width. And that large filter width basically destroys all the detail in the shadow. But like I said, we did not notice that until a few days later. For some reason, we just were concentrating on fixing the noise from the sky. And I will talk about how we fixed it in a couple of slides. So the next thing, I'm just basically showing you screenshots of various in-between development versions of our Quake 2 RTX. So the next thing was that we tried to adjust textures and tone mapping. First of all, like I said, the emissive objects in the scene were disconnected from the environment because they were all completely treated as emissive. We tried to fix that by applying a simple threshold function to the luminance of pixels in the emissive objects, and that kind of worked. Like if the texture luminance is greater than x, like 0.5, multiplied by 10, that works. Now, we also figured out that the textures are probably stored in some weird color space. Maybe it's baked as RGB, maybe it's something else, but it's not what you want to see in albedo. They are just too high contrast. And we tried to fix that by applying basically inverses RGB plus a few minor tweaks to the textures before feeding them into the path tracer. That made the picture much smoother. And the ambient lighting here in the room looks more natural for that reason. It's basically just very smooth. The next thing that we did was we added sunlight that brought back the contrast to the image that we lost by making the textures less contrasty. And that sunlight also adds visible diffuse global illumination. And when you move the sun, because nothing is pre-computed here, when you move the sun, you get all the dynamic GI updated in real time, and it's very cool to see. What we also did is that we fixed the missing shadows problem by separating the denoiser into two channels. Because, like I said earlier, we have this low noise and low intensity signal for the direct lighting, and we have a high noise and high intensity signal for the indirect lighting. So we just split that into two channels, and that actually worked really well. Finally, well, not finally, but next thing is we tried to do something about the materials. We tried various approaches like upscaling the original Quake textures with HQX or with various AI-based filters. We tried generating normals from the albedo or tried like deriving roughness from albedo, but none of that really works. What you want is actually physically based materials, physically based normal maps and roughness maps and specular maps. So what we ended up doing is we took the texture pack from the modding community from Quake 2 XP. Apparently, most of that was also used in Christoph's work. But we also added support for the other maps, not just diffuse, not just albedo. We added support for specular and roughness maps, emissive maps, which contributes greatly to the look, because instead of trying to figure out if that texture is maybe emissive, try to apply a threshold function, you just take a texture made by some artist and that acts as a light. That's very cool, and it works extremely well on some maps where most of the illumination is from local things like, I don't know, computer racks or whatever. And finally, of course, normal maps that help break up the surfaces, help make them much less smooth looking. Now, the next thing is that we added a procedural environment map to replace the horrible original environment maps from Quake 2. Well, horrible in the sense that they are very, very low res. We didn't have any artist-painted maps to replace them with, but we could do some physically based simulation of atmosphere. That's what we did, of sun color, depending on how the sun travels through the atmosphere, sunlight travels through the atmosphere. And we also added procedural mountains to the horizon just to fill it with something. And those mountains are actually pretty cool. They are fractal based and they react to the lighting in the atmosphere. That atmosphere is also HDR, so you get very bright lighting from the sky when it's daytime, because the sky is bright, and you get fairly dim and blue, like deep blue lighting from the sky at dawn. It looks very cool and natural. The sun color itself also depends on the position in the sky, and again, that lets us do things like high noon or sunrise or sunset, and they look different. And finally, of course, we added volumetric lighting, which is not really ray traced, but rather we ray march through a shadow map here. We render a static shadow map when the sky moves. It's just a very coarse kind of shadow map, 2K by 2K, I think, and we ray trace it because we can. We don't have to update it on every frame, you know. It was just easier to implement. We had very limited time there. So this is the kind of final image that we get from this renderer. This is the Q2DM6 map that we used in the keynote presentation a few days ago. But let's break it down into all the lighting components and how it works, how it travels through the denoiser. This is the raw output of the path tracer. It's actually a very, very difficult scene for a path tracer and for the denoiser to compute, because it's only illuminated by those bright spots of light coming from the sky, from the sun on the left. Everything else is dark. There are no local lights here. And for this reason, you get this very high noise picture with only a few spots of low noise sunlit surfaces. So this is the direct diffuse channel containing only the sunlight. It goes through the SVGF denoiser, very, very similar to one used in the original Q2VKPT. We just tuned it a little bit. And this is what we get out of it. That picture of snow in space is the indirect diffuse channel. It goes through a denoiser that is slightly different from SVGF because it's no longer variance guided. It apparently doesn't work. I mean, when you try to pass this kind of noisy signal through SVGF, it just doesn't really converge. It's not wide enough, and it always covered with those small patches of light in the result. So we removed the variance guidance, but we still are using the gradient samples to try and reject invalid lighting. Doesn't work great, but it's something. So in the end, we get this denoised picture. What's also interesting about it is that we project the lighting, the indirect lighting, onto first two spherical harmonics to get some directionality in it, because we have normal maps. And if we try to blur the indirect lighting over the surface with a normal map, we just don't have enough kind of surface to blur it over, because the surfaces are broken up with those lines on the floor and so on. So for the filtering, we use geometric normals, which are flat because the geometry is very simple here. But we work with those two spherical harmonics here. And then after denoising, we project the spherical harmonics lighting onto the actual normal map normal, and we get this detailed look. Although much of it is lost after we apply the textures, because that's how GI basically works. And the textures that we use from Quake to XP, however great they may be, they still have some amount of baked lighting in them, and that's very difficult to remove. Finally, we have actually a third denoiser channel, which is indirect specular, because we discovered that adding specular lighting to the direct lighting channel doesn't work well enough, because specular tends to be brighter, and it also tends to change more dynamically, because specular reflections depend a lot on the position of the camera. So like if you look at the light and you strafe around, it will invalidate a lot of the picture, and we don't want to do that with regular diffuse illumination, because that's actually perfectly static. So we separated the specular into its own channel, and we apply a purely temporal denoiser, very, very simple temporal denoiser to that. But again, it's guided by the gradient samples, so that we don't get that horrible kind of ghosting that you can get with a purely temporal thing. This is what we get out of the temporal denoiser for specular. Combining all these channels gives us that. This is just all the irradiance channels before multiplying them by the albedo. And multiplication by albedo gives us the final picture, of course. Overall, the pipeline looks like this. We start with the primary rays, which are separated into their own render paths. The reason for doing that, well, we have just basically a couple of reasons for doing that. One is performance. We can extract a little bit of performance that way because the primary rays are coherent. They are very efficient to trace. And we also want to make the path tracing shader much shorter, so that we don't hit issues like instruction cache hit rate on the GPU, because the path tracing shader is actually very, very, very long. So we separate that into a path. It actually could be replaced by rasterization. That would work, and that would probably save like half a millisecond at an ATP. But again, possible, but we didn't. Now, then we go through the path tracer, which produces a few channels. One of them is the transparent channel. Sorry, give me a second. A transparent channel that contains things like glass and particles. So the original renderer did not have particles in it, and we added that, and we do not need to denoise any of that, so that channel just is applied after composition. Now, the G buffer is pretty obvious. We have albedo and normals there. Indirect diffuse that goes through the spatiotemporal filter without variance guidance, but with spherical harmonics. Direct diffuse that goes through SVGF, and specular that goes through the temporal filter. After that, all the channels are composited on top of the G buffer, and then temporal anti-aliasing is applied. After temporal anti-aliasing, we have a few post-passes like God rays, that volumetric lighting thing, flow explosions, simple bloom pass to highlight bright objects, and tone mapper with dynamic eye adaptation. Now let's take a look at the updated path tracer. We start with primary rays, and let's just, as an example, assume that the primary ray hits the water. We can reflect off the water, or we can refract through the water based on some conditions like similar to stochastic sampling. So some pixels get reflections, some get refractions. And let's follow the ray that goes in the reflected direction. First of all, we cast a shadow ray towards the sun to determine the direct sun shadow, obviously. And we pick a random point on the sun disk to get the soft, airy light shadows from the sun. Second is direct light shadow that is very similar to what Christoph talked about. So we pick a random triangle from the list of direct lights in the sector, or we pick a random dynamic light. We actually replaced all the mesh-based dynamic lights with spheres, because that is much, much faster and it looks just the same. Now, we also have the bounce ray, which can be either diffuse, in which case it's cast in a random direction, or it can be specular, in which case we sample the GGX and DF and reflect the ray. Finally, after we find our bounce surface, we cast a ray towards the sun to get illumination, to get bounce in direct lighting from the sun. Or if we don't hit the secondary surface, we just get illumination from the sky. Finally, we have a ray that goes towards another local light for indirect bounce. Actually, we don't have a ray there because we don't do shadowing for indirect local light illumination. It just doesn't make any, well, it does make a little bit of difference visually, but it's not worth the performance. And finally, I would like to show you just some beauty shots of what we can get with this kind of renderer. This is just some water with all the reflection, refraction, and extinction effects, because as the rays go through the water, they also lose some energy. This is a look from under the water to the top. Again, some more water, some mountains on the horizon. Global illumination in an interior scene. Again, global illumination from the sky in an interior scene without the direct sunlight. Local illumination by emissive surfaces like that pool of weird transparent lava. Local illumination from emissive surfaces. These things on the pillars are actually not treated as local lights. They are not sampled by that stochastic triangle sampling thing. They are just emissive textures. And we sample those emissive textures when we cast a bounce ray towards the surface. And if that bounce ray happens to hit a surface with an emissive texture, that emissive color goes into the GI channel and goes through the denoiser. And again, some colorful local lights, base 2. Sunset, or rather after sunset, with some dark blue sky and local illumination from local lights. And this is basically a summary of almost all that we can do, including all the emissive surfaces, lasers, glass with reflection, refraction, sunset, mountains on the horizon, and all that. So some minor statistics and acknowledgements. This is our development team, or rather a list of people who contributed directly or indirectly. There's a lot of people here, and it was a very fun project because we had very, very little time here, just 6 weeks from early February when we started working on this to the keynote version this Monday. And a lot of people just wanted to contribute something, like either to implement one or other effect or to, I don't know, help with some modeling or textures. And finally, we would like to thank the modding community for Quake 2 XP for the weapon models, again, from XP that we use for other textures, and of course, its software for Quake 2 itself. Thank you.